Hi everyone, my name is Ricardo Parisotto, and today I present our work called ShadowFS, Speeding Up Data Plane Monitoring and Telemetry Using Before. This work will appear in the 2020 International Conference on Communications. Software-based paradigms are being used to rewrite the behavior of forwarding devices using software abstractions. One of the most popular languages for doing so is Before language. Before stands for Programming Protocol Independent Packet Processors. The language and also the concept of programmable data planes motivated many emerging applications to use the programmable data plane to process and analyze data, which enable faster reactions in contrast to mirroring packets to middlebox or controller-based applications, which were the standard approach for software-defined networks. Telemetry monitoring is one of the tasks that can benefit from data plane programmability. However, many operations on forwarding tables may become slower if using forwarding devices. A solution to that is caching table entries into smaller and faster tables, but traditional cache replacement mechanisms does not consider important factors of the data plane, mainly because they are not designed for forwarding devices. Additionally, current work are not targeted to monitoring telemetry scenarios, which incurs in higher overhead for non-monitored flows. In this work, we propose ShadowFS. ShadowFS extends our previous work called FlowStalker. It's a before-based telemetry mechanism. The ShadowFS cache monitored elements into a faster table and proposes a new language operator for before to abstract how the caching and the monitoring occurs. Dynamically, the system leverages monitoring metrics to cache frequent entries into a smaller and faster table. Now, we'll describe some background on before language. Before is a high-level data plane programming language. It divides the behavior of forwarding device into three main blocks: a parser, a pipeline of control flows, and a deparser. The parser is a state machine where the programmer declares names for each header field, so the parser can reference bit fields into typed data of the language. In practice, states of the parser correspond for packet headers, and transitions are transitions between one header to another. After the packet is processed by the packet parsers, it falls to a pipeline of control flows. Control flows are composed of a set of logical match action tables, which are defined by the developer. An apply block specifies semantics in order to process header contents and modify the content if necessary. After a packet and the processing of control flows, it follows to the parser. The parser writes internal variables to the packet header and emits to output port, or recirculate back to the parser. Now, we'll describe ShadowFS. ShadowFS builds on FlowStalker to offer a solution for speeding up data plane monitoring. FlowStalker is a two-phase monitoring mechanism that monitor per flow and per packet metrics in the data plane. When a flow crosses a threshold, it sends a warning for the control plane. The control plane then collects data using telemetry. It sends a crawling packet that traverses the network and collects data, and then go back to the control plane. ShadowFS stands for FlowStalker. It instantiates monitored modules to watch forwarding tables. After collecting data, it ensures that frequent flows hits a table with fewer table entries. The reasoning behind that is that the lookup time in programmable suites is proportional to the number of entries in tables. Therefore, tables with too many entries may incur in high overhead in processing packets. Design principles of ShadowFS are divided into 4 different modules. First module annotates before programs to specify which tables will behave with a cache. Next, we split tables to behave with a cache. A control plane API enables network operators to modify the content of tables. And finally, a hot swapper module keep hot swapping hot items into a smaller and faster table. This figure presents the architecture of ShadowFS. Next, we will present each independent element in detail. Aiming to making our system transparently for the network operators, ShadowFS provides an extension for the for language to specify which table will behave with a cache. The figure presents an example of a IPv4 table called IPv4 LPM that has an additional parameter called host shadow. That the parameter 18 means that the cache table for IPv4 LPM will have 18% his original size. After specifying which tables will behave with a cache, the program goes through a preprocessing phase that splits assigned tables into logically separated tables, the main table and the shadow table. The main table will be actually the specified table. The shadow table is a copy of that, but with the size corresponding to the parameter passed by the specification. The control flow of the final program will try to match the shadow table before matching the main table. If the packet matches the shadow table, it follows to be monitored. Otherwise, it follows to the standard switch behavior. If the packet does not match the shadow table, then it follows to the main table. If it matches the main table, it will follow to be monitored. Otherwise, it will follow to the standard switch behavior. After parsing the IPv4 code, then building the final program with the cache, ShadowFS builds a programming interface for the control plane. This programming interface will operate in a transparent manner. This means that the network operator will add flows, remove flows, and get monitored statistics without need to know how the monitoring occurs or if the table will behave with a cache or not. ShadowFS must be able to keep the frequently monitored items into the shadows. The shadow table is smaller and keep fewer table entries. Therefore, it will provide a faster lookups. To this, we use an additional module called hot swapper. Hot swapper cannot operate entirely in the data plane because it requires to rewrite the table entries. And data plane does not enable to self-write before table entries. So the hot swapper is a hybrid model. It operates part in the data plane and part in the control plane. Data plane part is based on flow stalker. It monitors models to store per flow metrics. It stores timestamps and hit counts for each monitored table. It's actually an instance of flow stalker. These monitored items are used to ensure that frequent table entries are in the shadow. To this, hot swapper always insert table entries in the shadow table and hot swap non-frequent items to the main table. To perform the hot swapping without disrupting the normal packet forwarding, we must ensure that the packet does not see intermediary states. To this, updating or hot swapping must be performed in the following order. If you are inserting a new table entry in the shadow table and the shadow is full, first we need to decide which are the tables that are non-frequent. We copy that entries into the main table. Then we can free space of the shadow table and deploy the new rule. Note that this will occur transparently for the operator. It may insert new flows without knowing how this mechanism occurs. Now we'll describe experimental evaluations of ShadowFS. We deployed ShadowFS into behavior model. It's a software switch, and we performed a few simulations to measure throughput. To measure throughput, we do not care for end-to-end metrics. For example, we do not care for the time for a end host to reach the switch or the switch to reach the end host. We just want to evaluate the processing time of the switch. To this end, we store local timestamps in the beginning and the end of the pipeline. These timestamps are stored in registers. And after our experiments, we collect these timestamps and measure throughput. First, we want to show the worst case scenario for ShadowFS, which we aim to quantify the overhead. The worst case scenario is that we specify tables that will behave with cache and only have one table entry. In this case, throughput decreases with the number of watched tables. This means that as we increase the number of tables that will behave with a cache, in this worst case scenario, throughput decreases. However, when a monitor table has too many entries, we can clearly see the benefits of ShadowFS. We annotate a layer 3 router and fill the tables with table entries. And we can see that throughput increases when traversing the shadow table. So in a scenario that we have to monitor flows, and there's an increasing number of table entries, Flowstalker and ShadowFS may enable flows to be processed with higher throughput. This work represents a ShadowFS, which is a cache mechanism for programs. It specifies tables that will behave with a cache, enable frequent entries to be processed with a higher throughput. ShadowFS still has a few limitations. First, we do not perform any real hardware study case. Also, caching into different devices may allow better use of resources. Finally, determining intervals between hot swapping table entries are also in perspective for future work. This work presented ShadowFS. Thank you for watching.